Yeah, thanks for the invitation. I appreciate the chance to be here. So I'm going to talk for a few minutes about the whys and how that they do this kind of work, and then Steve's going to come up and talk specifically about the data they've collected and the results of the project over time. So I'm going to start with a few minutes on just why you go after harmful algae blooms. This is an increasing problem all the way across the United States. The lakes are the lowest point on the watershed. Nutrients and sediment things might eventually over time migrate downhill and end up there and just accumulate. And in our case, the nutrients that drive algae growth, and I'll talk about species shifts a bit in a minute, as lakes age and you get nutrient levels go up, there's a species of algae called cyanobacteria or blue-green algae that actually produce toxins. They produce two acute toxins, one's a liver toxin, one's a neurotoxin, and you hear quite often about dogs ingesting water at a park and stuff, and these are pretty fast acting. They can be lethal. There's also cases across the country where a good case in New Mexico a couple of years ago where a bunch of people came out to a wilderness lake and they found 400 or 500 dead elk laying around the lake, and it was directly attributed to them ingesting these things. They also are finding that they're producing chronic toxins. There's a couple of compounds that are produced by these species of algae that are directly linked to ALS or Lou Gehrig's disease. And so that's the reason you want them out of your lake, basically. So I don't know how that happened. So I just went real fast. There are a couple of reactive strategies you can use. There are EPA registered algicides that you can come in and use on a case to clean up a lake that's got one of these problems. The City of Canyon Lake's going to be looking at evaluating a couple of these over the course of the summer to see if there's any opportunity or need to use them or have a fit. Just a couple quick case studies we've been involved in. Lake Wilderness is a lake up in Washington State that had an Ironman event scheduled, and he's bringing people from all over the world. There's a swimming leg, there's a biking leg, and a marathon leg. In this case, about a week before the event, there was a cyanobacteria bloom that was producing microcystin, which is one of these toxins. They measured it. They were basically freaked out. What are we going to do? And we were able to come in with one of these peroxygen algicides on Thursday before the Sunday meet, treat the north half of the lake. The county came back and did the sampling the next 2 days, and the toxins were basically gone. So they were able to have the event. Another case is a little closer to here. Lake Silver was the terminal reservoir for the east arm of the California Aqueduct up in the mountains in San Bernardino. About 5 years ago, they had an Anabana bloom, which is one of these blue-green algae species that was producing toxins. They couldn't deliver water to 4.5 million people. So we came in and, again, did an application and cleaned it right up. So that's just to point out that there are some reactive strategies that you can use if you're in trouble and need to get out of trouble fast. We're really going to talk about here, though, is nutrient inactivation. Plants, algae are plants. They need nitrogen and oxygen to survive. You look at this graph, I don't know if you can read it, but on that side of the graph, at the upper axis, that shows different species of algae. So those colors you're looking at there are different species. So if you're way down on that end of the scale, the bottom part of that scale is actually phosphorus increasing as you go to this way. So if you're at the bottom end of that, you see you've got all kinds of different, you've got good species diversity, you've got all kinds of beneficial algae in there. And if you notice, as the phosphorus levels increase in the lake, the blue one on the bottom that you see that gets bigger and bigger and bigger, that's cyanobacteria. And these things are unique that they can fix the nitrogen they need from the atmosphere while the other algae species can't. So as your phosphorus numbers go up, the competitive advantage goes to those guys, and they tend to bloom, and the more cyanobacteria you have, the more potential you have for toxin production and that type of thing. So that's kind of what the idea is there. So ALUM was first developed under the Clean Lakes program. When the Clean Water Act was passed in the 70s, there's a section 314 of that act that allowed researchers to go out and really look at in-lake restoration strategies, and that's where ALUM came from. It was developed in the 70s. We worked on a couple projects back east where some of the first ALUM applications were done in the country. And ALUM is it's a product basically that's applied to the surface of the lake. It forms a flock, and as the flock settles down through the water column, it captures anything with a negative charge. And things that are negative charge are clay particles, phosphorus molecules, and things like that. So as it's going down through the water column, it's capturing the phosphorus and stripping it out. And as it settles on the bottom, it sort of forms a blanket in the deeper water areas that catch the phosphorus that might be releasing from the sediment and going back into the lake column. So that's why it's used. So Canyon Lake, we started doing this about 10 years ago. It's a 500-acre, well, you guys know all this, it's your lake, right? It's a 500-acre reservoir. You had a TMDL set for phosphorus that had numeric targets. We won the RFP to come out and do the work, and we've won a couple since. But basically, the operation is we bring the element in tank trucks, we put it into a boat, we have GPS controlled sections of the lake that based on the water depth under the boat, we run back and forth. And there you can see just a flock kind of forming up and passes maybe the boat, and that'll settle out of the water column pretty quick and take the phosphorus with it. If you think back to that graph, what you're trying to do is you're trying to push the phosphorus numbers way back to the other end of that graph where the cyanobacteria don't have a competitive advantage and where the other beneficial algae that might be an important part of the food chain can really thrive. Just another quick example of a lake up north. This is kind of similar in that they were looking at a capital cost. They had a hypomagnetic aeration system in this lake for 20 years, and about 10 years ago it failed. And they were looking at a capital cost of replacing it of about $3 million versus trying to deal with the nutrients in the lake, and their engineering groups kind of came up with the same kind of a conclusion. It would be more cost effective to come in and do in-lake phosphorus mitigation, and they've saved quite a bit of money. So it's just another quick example. Just the last few slides before I hand the mic over to Steve. In Southern California, in a lot of parts, alum, when the pH gets high, there's a couple chemical reactions that can take place that make alum a little less, it loses its ability to capture phosphorus. So if the pH in your lake is higher than, say, 8.5 to 9, you start getting up in the range where the thing crashes off and doesn't work as well. There's kind of two ways around that. One is you use a lot more alum because it's a little bit acidic and you can reduce the pH. A second technology that came along about 10 years ago in the United States is the use of lanthanum. This is something we've used pretty successfully over in Orange County and a few other spots. And the differences are lanthanum is a rare earth element, it's mined. It's applied the same way you would apply phosphate, but when it bumps into a phosphorus molecule, it forms a new mineral called ribdiphane as it sinks, and that molecule basically is never biologically available again. And it kind of does the same thing. The big differences are, though, is the water quality you're putting it into doesn't have any kind of impact on performance, and putting it in the water doesn't have any impact on water quality. Alum, if the lakes, this doesn't happen much around here, but there have been cases of fish kills from alum applications because the lakes are really soft water, and you put that much stuff in, the pH can move around to the point where you have problems. So that's just maybe a kind of a quick case study on what you would useful, maybe it's an option where you've got higher pH water. So this is a case study. It's one lake in Washington State where we work on, this is the third year we've done lanthanum applications on this lake. Same thing, cyanobacteria problems. We put a budget together, just a picture of the application going out. It goes out just like you put alum out. It kind of settles through the water column. And this is just quick results. SecuDisc is a measure of transparency. So it's a disc you lower down, and you can basically lower it down and try to see how deep you can see it. And the faster you can't see, the less stuff you have between your eye and the disc, the clearer the water is. It's kind of a measure of biomass or population. So pre-treatment, they had SecuDisc readings that averaged 2 to 3 feet. After the first year of treatment, decreased pretty dramatically. SecuDisc readings were up in the 6 to 8 feet. Last summer, most of them were around 20. We had a few that were, got storm events or something right after that, but the average was about, so basically we totally cleaned up the population there. The phosphorus numbers were under 20. Well, free reactive is pretty low, and then the total phosphorus, 20 is kind of a benchmark for a clean lake, I guess, and that was able to be maintained. The hypomagnetic phosphorus, which can accumulate in the lower part of the lake below the thermocline, over the last 2 years have been dramatically reduced. The green bars you see there were the first year we treated. We did a treatment in May to strip the water column. We did a second treatment in August to capture the stuff that was building up in the lower part of the lake. The 2021, you see the blue bar there, it's still sort of the same pattern, but it's way low. And that's just kind of an end result thing. So in conclusion, basically there are tools that you can come out and deal with an emergency. There are reactive solutions that are available for use, but targeting nutrients in the lake, I think, is a real benefit in terms of, you know, effectiveness and cost effectiveness. When I was, the North American Lake Management Society is a group of people like ours, and one of the things their scientists have given papers on year after year is that there's a lot of money spent in the watershed for BMPs and things like that, but a lot of times nothing changes in the lake. And so it's just a component of, you know, this is one tool in the toolbox that gives you some options to kind of work there. So Steve, you want to take over? Maybe we'll wait for questions till he's done.